Welcome back, everyone. We're going to be beginning our third section of Chapter 12, which, up until this point, we've been talking about how gravity exists in between two objects, and then how some objects may be attracted to the Earth, and how gravity varies depending on how far away you are from the Earth. Now we're going to be talking about how bodies actually orbit other astronomical bodies, in most cases the Sun. And so I'll just draw the Sun right here. And we usually think of, there's a sun with sunny rays shining out of it, right? And we're used to seeing in textbooks the fact that objects orbit the Sun in circular orbits. Well, as you probably know, that's not the case. They don't orbit in circles. They actually orbit in ellipses. And so in reality, and I'm going to exaggerate this quite some bit. If this is the Sun right here, a body orbits it in an elliptical fashion. Now what I'm going to do is I'm going to put another mark right about right here. Okay, so you can just see that. And this body is going to be orbiting the Sun. Now I can't freehand this very well. It's going to be orbiting the Sun and this other mark. And this orbit, this very non-circular orbit, we call an ellipse. Now this, the point where the Sun is and this other point where nothing exists, both of them are called a focus, and the plural of that is foci. But each of these things is a focus. There and right there. And both of these foci, depending on how far apart they are, determine the shape of this ellipse. But I'm getting a little ahead of myself right now. I just want to point out some astronomical terms, first of all. First of all, we have astronomical unit. And this is simply the distance from the Earth to the Sun. Now, the Earth, just like every other planet, orbits the Sun in an ellipse, and there are times when it's further and when it's closer to the Sun. We're going to call these, we'll give these close and far names, these close and far locations named in just a second, but the astronomical unit is the average or the mean distance from the Earth to the Sun. Again, I said over here that I really exaggerated this ellipse, and in most planets actually do orbit the Sun in fairly circular orbits, and they're not as exaggerated as that. But since the Earth's orbit does vary, we have this 1.5 times 10 to the 11th meters as our average or our mean distance from the Earth to the Sun, and we call this an astronomical unit, or an AU. We take this and we use this as kind of our meter stick for the rest of the solar system. So if we have a planet that is I don't know, 5 times from the Sun the distance that the Earth is, we say that it's 5 AUs away. So we call that an astronomical unit. Okay, so now we get to these strange terms here, periapsis and apoapsis. What I'd like you to do, just for the time being, I do want you to know these terms, but I want you to ignore the second half of it. I want you to ignore the suffix here and just look at peri and apo. Now I'm going to draw another ellipse down here, down below, and hopefully it's fairly, well, that's not going to be very good. Well, that's not too bad. Nope, it got bad at the end. Anyway, it should be an ellipse. And as you remember, like I just said, we have the body that's being orbited, in this case, let's say it's the Sun, at one of the two foci. Okay, and this other focus right here, nothing is at, but it exists in space. And our orbiting body, heck, we'll just say it's the Earth going around the Sun. You can see clearly that at some point it's going to be very close to the Sun, and at another point it's going to be very far away from the Sun. These are the two terms that these are the two locations that these terms refer to. Periapsis means, or peri anything, means the closest approach. So from here to here, we're going to call that the periapsis. apsis. And the reason I told you to ignore this, the second part, the suffix, is because the suffix may change. For example, periapsis is kind of a generic term, but the Earth going around the Sun, we would really call this perihelion, because Helios was the god of the sun, and anything helion means sun-related. Or the Moon going around the Earth. The Moon goes around the Earth in an elliptical orbit, and when the Moon is closest to the Earth, we call that perigee, like Earth, geo, okay? So the suffix may change, but the prefix is going to be the same. Peri, anything means closest. Think of a periscope. A periscope in a submarine. What a periscope does is you look out of it and it brings objects closer. Well, it makes the objects appear to be closer because it magnifies them. So we call that periapsis here. On the contrary, over here, this whole distance from the Earth all the way out to here, we call this apoapsis. A-P-O-A-P-S-I-S. And there's probably some sort of Greek or Latin root that ap or apo means away. But if you can just remember that peri means close, like periscope, makes things look closer, then you remember that apo means further away. But the same thing, Earth going around the Sun, aphelion means furthest from the Sun. And the Moon going around the Earth, apogee means furthest from the Earth, furthest from geo. Okay? So there's a few terms there to kind of get us started. Which brings us now to Johannes Kepler's first law of orbits. And what we have here is actually a very well-drawn ellipse. And I want to label a few parts of this ellipse right here so that we can recognize them when we see them again. Part of this I already mentioned already. The fact that the Sun exists at one focus of an ellipse. A focus right here, and right here is where the orbiting body is one of the two places the orbiting body must exist at. In fact, I'm going to undo that there. There's nothing here, but the Sun is right here, and so this body orbiting the Sun will be going around much like this. And you can see right here we have perihelion, closest to the Sun, and aphelion all the way out here, furthest from the Sun. And a very important dimension of this is what we want to call the Semimajor Axis. And the Semimajor Axis exists not from a focus to any one point, but really from the center of the whole ellipse all the way out to the edge. That's the Semimajor Axis, and we're going to call that A. We're going to call that A. We're going to give it a name a little bit later. Okay, but that is called the Semimajor Axis, and this is generally the, if for any planet or any orbiting body, this is the distance that we say that it is, well, we say that is kind of like the radius of its orbit around the Sun. It also happens to be the average distance from a focus to points on the ellipse. Now, our focus, the Sun, for example, is right here. Well, we have all different varying distances from the focus to points on the ellipse, but that Semimajor Axis is the average distance. So A, this is going to be very important. The Semimajor Axis. All right. Let's go on to our next slide. Orbital distance at apoapsis and periapsis. Well, this also brings up another point to us, or another term to us, called the eccentricity. And the eccentricity is, you might say, a measure of the elongatedness of the ellipse. This right here is an ellipse. This right here is an ellipse. All of them are very poorly drawn. This right here, I need to round that a little more, but you get the idea. They're all ellipses. But what makes them different kinds of ellipses? Well, this one has the foci fairly close together. Here, the foci, the focuses, if you want to say, are further apart, and they're further apart even here, making the ellipse more flattened out. there's multiple ways to calculate the eccentricity, but we're going to use it this way. By the way, before I go any further, we should say that a circle is kind of an ellipse. Let's just pretend this is going to be a perfect circle right here. Okay? Well, the two foci are right on top of each other in the center there. So it doesn't have any eccentricity. It's not elongated or flattened out at all. It's a perfect circle. So you can see here on our diagram we have right here RP. What do you think that means? Well, that's the radius, or the perihelion radius. And this right here, RA, well, that's the aphelion, or apoapsis radius, all the way out here. And then you got these terms here, EA and EA. This is really a measure of the eccentricity. The further and the flatter an ellipse is, let's say this right here is the very center of the ellipse. Well, the further and flatter that it is, the distance from the center to one focus and the center to the other focus is going to be getting greater and greater and greater. Here's the center, now the focus. Distance is here, and here's the center, of course, the focus. Distances are much closer together. So what we care about is the fact that the apoapsis or apogee or apohelion radius is going to be equal to the semimajor axis. Remember what we said that was? That was from the center all the way out to the long edge, or the long end of the ellipse. That's A, our semimajor axis, times 1 plus the eccentricity. Okay, and our perihelion or perigee or periapsis radius is going to be equal to the semimajor axis times 1 minus the eccentricity. And again, this eccentricity is right in here. If we wanted to factor in this A, it would look like this. Our A, the aphelion radius, would be, it's already been factored out. Let's distribute the A. Would be A plus A times the eccentricity. And the perihelion or periapsis radius would be A minus A times the eccentricity. And think about it. I drew all over this, and hopefully you can see it. This whole black line is A. And if this right here is a measure of our eccentricity, we take that away, and all we have is this distance right here, which is our perihelion radius. Up top here, our aphelion radius. That would be A plus AE. Again, all this from here all the way out to the edge, that's our A. And if we add from here to here, that's our AE. Again, I realize I marked up all over that, but all this plus that is our aphelion radius. One more slide before we actually get into some couple examples.